enjoy the department.
All right. I think I'm recording. Recording, right?
Yeah, it's recording.
Okay. So I apologize. You guys are gonna have to endure another tutorial from me, a person who has no idea how to give tutorials.
You have a
But
You do great, Rob. Don't talk about yourself like that.
thanks, you, Tetson. But I'm trying to get better. But the good news is this one's going to be short today. Because I wanted to give a little bit of an overview over like a little tool I published on GitHub recently. I think maybe if even one person finds it useful, then sweet. That'd be great.
This is a you thing.
You made this?
Yeah.
Oh, we'll definitely use it.
Basically, I just want to first start off like when I say the crystal structure of a protein, I feel like most people don't really know what that is.
Unless they've taken 3381.
Unless they've taken 3381.
And they happen to have not forgotten.
Yeah. Because there's actually a difference between a crystal structure and just a structure of a protein. The most obvious difference being that it was collected using a very specific technique, which is X-ray crystallography. But there's actually more to it, and I kind of want to go over that. So if we go to the PDB and we just download a crystal structure, so we'll take the 9OM8. This is our structure of one of our structures of PPRA, right? So we can just download the PDB file, and then if we open that up in PyMOL, this is what we'll see, right? So when most people think of a crystal structure, they'll think of this. It's like a structure of a protein. In this case, this crystal structure has 4 copies of PPRA. They're labeled here in different colors. And you might also know that, well, the structure that you downloaded from the PDB, really all it is like the XYZ positions of every single atom in that protein. So we could look at that, show has lines. And so right, you can see like every line is just an individual atom. Okay. And so that file that you downloaded from the PDB, be it either in a CIF format or PDB format, what it really is it's just a text file. It's just a big long text file. So you could take that file and open it in any text editor you use. And what you'll see is just thousands of lines, and every single line represents the XYZ coordinates of an atom. So for example, like here is nitrogen. It belongs to isoleucine on chain A, residue number 13, and then these 3 numbers here are the X, Y, Z positions. And then here you have something called an occupancy, and finally you have a B factor. Don't have to worry about what those 2 mean, but essentially just it's a big long list of X, Y, Z coordinates, which together make up a crystal structure. Now, the difference between a protein structure and a crystal structure, believe it or not, is this single line up here. That's it. It just starts with crystal1, and then you have a bunch of numbers that come after it. Right? If I were to delete this line, this is now a protein structure. Now it's a crystal structure. Really, that's all it is. So let's unpack what this header means. If we open up this file in PyMOL, PyMOL kind of interprets this crystal line, and then it knows what it means. So let me do this. Maybe I'll do this. Maybe I'll Okay, So those first three numbers, we have 298, 44, 89. So those actually represent the unit cell diameter, or the unit cell parameters. So we can visualize that in PyMOL. Right, so if we've got, this is what that unit cell looks like. So we have 298 angstroms in one direction, 44 angstroms in, I believe it would be this direction, and then 89 up here. And then, oops. The other numbers, 90, 106, 90, those are just angles. So you have 90 degrees, 90 degrees, and then 106 degrees, which is, I guess, that one. And so with those 6 numbers, you can describe any unit cell out there. Okay, so this still doesn't really look like much. This is still just 4 copies of PPRA and a unit cell. So there's one.
Just to remind people, so the unit cell is the basic repeating unit of the entire crystal, which you can recreate the entire crystal simply by translating X, Y, and Z. So literally the most fundamental repeating, translatable repeating unit.
Yes, question. Would there be more than 4 copies in the unit cell? Because I feel like that's a lot longer.
That's a great question, right? And so, yeah, so the question was, there's only 4 copies here, but there's this giant unit cell. Like, that doesn't make any sense. There's a lot of empty space.
You'd never form a physical crystal.
Right? This doesn't look like a crystal at all. So that's where this last piece comes in, C121. So what that is something called a space group. So a space group comes from this mathematical theory called group theory, which basically says that any 3-dimensional lattice, you could take any lattice of whatever, and it could be described with a finite number of symmetry operators. And what does that really mean? So you could take either a crystal lattice, or you can tile a driveway or some tiles or whatever.
Literally, like Alva and I, when we were postdocs together, we used to go around and think about things that we would see and see what space group.
Oh, look over there. There's a C121.
Yeah. Yeah, exactly. And so for I think a solid few decades, it was really just like a matter of stamp collecting, where mathematicians just went and figured out, oh, there's actually this space group that we haven't figured out. Oh, there's this other one. And I don't know if anyone's proved that what we have now is a full, complete set, but I think the consensus is that we've discovered all the unit cells, all the possible ones. And so there's, right now, I think the list is at 230. And so there doesn't exist, to my knowledge, any lattice that doesn't fit into one of these groups.
Oh, skill testing question from 33.1. What point group is not present?
It's been a while.
I don't know this.
P5.
Oh, yeah. Bifold symmetry is a quasi-crystal.
Yes, that. I remember
That
now.
was a multiple choice question.
Oh, I had no idea what you were asking. You said
So if you look up there, there's all there's 2s, 3s, 4s, and 6. There's no 5.
I still don't get why there's no 5.
Yeah, you can Google it on.
There's do you ever watch Veritasium
Oh, I
on
love
YouTube?
Veritasium.
He has this one video about tiling, and he actually goes into it where he makes tiles that have 5-point symmetry. And so you could start tiling, and it looks like a normal crystal. But then eventually you reach a point where, wait a minute, there's a gap here that I can't fill.
Yeah.
And there's no possible way that you could put it in. And so it looks like a lattice, but really it's a pseudo lattice because eventually it's going to get truncated. And so there's no way for you to tile it to infinity. It's like a finite lattice that you could do. It's just a property of like fivefold symmetry.
So what do P5 crystals usually look like then?
Actually, recently they grew quasi-crystals and they showed that you can get diffraction from it, but you can't. Yeah.
That's all.
That's where all the DNA ligands end up in the gap.
I was,
No, into protein.
I was thinking, it's like,
It's pseudo fivefold.
at least my understanding of like what crystals could be, there's some impurities in crystals, no? Like
Yeah.
so like, wouldn't those little gaps just be like impurities that you can maybe get around?
It's important that way, but
Okay.
but so well, the part that always sort of frustrated me is that, well, you can divide 360 by 5 and get a an even number. It doesn't seem inherently like it would be a problem because like it's not like an odd number or something. But that's not the issue. It's a package.
But the cool thing is you can grow if you control everything perfectly, you can get these fivefold lattices that'll eventually truncate. There's a limit to how big they can get because of math. And you can diffract X-rays or electrons or whatever through them, and you'll get a diffraction pattern, but you'll never be able to solve it because the maths assume that it's an infinite lattice, whereas this is inherently not. But anyways, I know this is like very recent that they managed to do that.
I'll have to be careful on what I say in class because someone will catch it. These guys are good. I find myself going to chat more frequently to figure some of the questions out that they send me.
But it is true that there's no space group for fivefold symmetry. Okay, so in this particular case, right, we've got the space group C121. So I could send everyone a link of this, but this is like a little.
It's giving me anxiety again.
I'm not going to even attempt to explain what this means because I don't know.
I love
Number
it.
one. But what I do want you to see here is that each space group has a set of symmetry operators. In this case, we have 4. Here's this one, this one, this one, and this one.
If you ever get stuck, Han Wing and Brian Shelton can this stuff up. They're classically trained. They know this stuff inside.
Yeah.
Ong was teaching us this math stuff in a third-year methods class for crystallography, and it scared me to death.
So I don't really know how to interpret these operators really, but just know that there's like each space group will have a certain one. Like P4 will have like 12 symmetry operators. C1 and C2 will have 4 symmetry operators. So what does that mean? So every space group is always going to have this first one. This is called the identity operator. All it really means is just take your coordinates and do nothing to them. Just leave them alone.
That would be a P1 space group.
Yeah. So a P1 space group only has the identity operator, and that's it. So let me show you. So this, for example, let's get rid of this. Right. So P1 operator gives us this. Right. No change. So now we have the second operator, which I think what this means is flip along the x direction and then flip along the z direction in a mirror plane. So 2 mirror planes cancel out, and what you end up having is that.
Is it a reciprocal when we say flip?
I think it literally means reflect. So if you notice, like every crystal lattice, or every protein crystal lattice is only going to crystallize in a space group that has 2 mirror planes per symmetry operator. Because there's no, like if you do a mirror reflection of a protein, then you're going to break chirality.
Yeah.
And proteins are always chiral. So if you do mirror reflection, that can also be described as a rotation.
Okay.
Anyways, that's another symmetry operator, which
small molecule crystallography is like a whole lot crazier.
Yeah.
Crazy.
Because you have
Because you don't
mirror
have a chirality problem, like it'll just.
And there's glide planes.
screw axes.
Yeah, it's way worse.
But yeah, what you'll find is proteins tend to crystallize in like a pretty small subset of space groups for this reason, right? Because they're limited by chirality and other geometric things. Okay, so anyways, that's the second one. Next one, we have translation along the unit cell by half unit in the x direction and then half unit in the y direction. So it basically will look like unintuitively like that.
Seem to be leaving the unit cell more.
I know, so we'll get to that. So
Not the direction you were expecting.
Yeah, no, I thought we were going to the left. I was trying to imagine.
Well, okay.
I thought there would be like 8 little pockets around the corners, but I was wrong.
and then we have the final one, which just looks like that. Okay. So now we have a full description of the unit cell. So like you said, it still looks like it's outside of the unit cell, which is
I can see how it would fit into the unit cell
Yeah.
if it were to be moved, but
now. Has anyone played like those like really old school like Nintendo games where it's just like a platformer, and when you like run off of one end of the screen, you appear on the other end?
Yeah.
So if you picture that happening here, right? So the atoms that are coming out of the unit cell, they just appear on the other side. So we can do that transformation.
What a
Oh yeah,
beautiful analogy.
let's do that. Let's do that one at a time, actually. So let's do that for the zero operator. So we'll just wrap it. Then we'll do that for the one operator. We'll wrap it over. Same with this one. And same with this one.
I feel like this
So
is
it's-
witchcraft.
So it's all the same atoms. They've just been kind of wrapped around. So you can see this is like the full unit cell now is completely filled. And I think in this case we have what's our volume? This was
I do have a question.
Yeah.
Like, so your analogy was that like it's just coming around to the other end, but that is no longer now the shape of the so like
So why did they define it that way
Yeah.
rather than just based on how they're stacked?
So because when you're talking about proteins, it's a lot easier to visualize the full intact protein molecule rather than visualizing a piece of one here, a piece of another one here, and a piece. So it's the same description, just like for our convenience.
So like say there was all the other proteins around it.
Yeah.
Right. This is a snapshot of all the proteins as they fit into the unit cell, even though it's not full proteins fitting into the unit
Okay,
cell.
let me kind of here. I'll jump the gun here, actually.
Okay, so yeah.
Right. So you have. Let me.
This makes so much sense now.
Right. So you have like the one that's extending out to here really is just extending over here.
Mm.
So you're just kind of, it's just a different description. Right, so essentially, so this is now, so now that we have, so now that we have this, all we need, we now know the position of every single atom in the entire crystal, in theory. I mean, proteins aren't, or crystals aren't that perfect, but let's say you were some like crazy mad scientist that found some way to make a perfect crystal. In theory, you can now pinpoint the exact XYZ coordinates of every atom in that entire lattice. Because all you do is you take this unit cell and you just translate it. So no rotations, no nothing, just pure translations.
And that creates the physical crystal, the actual crystal that you.
Right? And so
That's how it physically the proteins are packed together.
And so if we were to extend this out, eventually I would crash my computer, but you would arrive at the shape of the crystal that is in your drop.
Am I remembering correctly that the shape of the crystal is also the shape of the unit cell?
No, it's not that simple.
Yeah.
Not always.
Because
Okay.
sometimes it'll like, maybe it'll pack, or the protein will pack easier in one direction, but not, it's like less likely to pack in this direction, so.
It can be hard to tell. Usually though, the ones that are sort of rectangular, they're fairly easy to pick up.
But I know that the angles are preserved. So the lengths, not so much, but the angles of between the faces, those are conserved.
Is that why you can get different space groups from the same protein? Like DDRC, the other group had a different space group than us.
So that one, what you're thinking of specifically is it really was a fully different packing. So it wasn't. But to kind of expand on what you're saying, there can be multiple ways of drawing a unit cell in the same lattice. So like here we have a C1 based space group, but we can very easily do like a P1, for example.
You can always do P1.
Yeah.
Always. It's never wrong to do P1. The only reason people avoid it is because your number of observations drops.
Yeah.
If you have to account for a lot more parameters to define. So,
because when you have a lot of symmetry operators, that kind of limits what you have to, I guess, the positions of the atoms that you actually have to solve. If we were to, right now, this has 4 copies in the asymmetric unit, but 16 copies in the unit cell. So if we solve this in P1, then we'd have to solve all 16 copies, which would be a lot.
you can use something called crystallographic symmetry to help compensate for that, but it's actually a little less precise than perfect symmetry. Anyway, yeah, so it's always best to use the highest symmetry operator possible that gives you a solvable structure.
Okay, so anyway, so that's like
Crystallography.
the kind of crystallography 101. But you might be asking, like, okay, how did I generate these? Surprisingly, PyMOL and all the other like popular molecular visualization software don't have something like this built in, even though they're made for looking at crystal structures, which is kind of surprising. They have some like generate symmate functions, but they're kind of crappy. So I kind of wanted to make a script to do this automatically because I found myself just doing it a lot. So let me just give a little tutorial on how to do this. I can give everyone this link, but I uploaded this to GitHub, calling it Lattice Explorer with a nice little ChatGPT made logo.
Something like
That looks really good.
Lattice Explorer.
But basically all you have to do is just download this Python file. That's it. There's just one file, and it's just a PyMOL script. So if we just go download.
Also, what is GitHub?
GitHub is a place where like people upload code.
Oh, okay.
Like a
Yeah.
data bank kind of?
Yeah, it's basically like a data bank. So
It's a code data bank.
yeah, essentially.
Is this a PML file? Or how
This
does
is a .py file.
Okay.
So .py is also just a text file, and it just has like a bunch of instructions for PyMOL on what to do. So if we open up PyMOL, there we go. Just make this easier. All you have to do is file run script, and they'll just ask you for the file. So if we just select that file, boom, and we just open it up. So I just made a little GUI to make things easier.
Thank you. Always appreciate it.
So you start off with basically 2 options. You can either load a crystal structure from file, let's say you just solved one and you haven't deposited it yet, or you can pull one straight from the PDB code. So maybe let's just pull one. Let's get 6 BDU.
That sounds familiar.
I feel like I'll be
PPRA.
using this for the rest of my life.
And then before we click Generate Lattice, what you do here is you have to select a unit cell expansion. So that just says how many times to translate the unit cell. So if you select 0, it's just going to make a single unit cell. If you do 1, it's going to go plus or minus 1 in every direction. So let's just start with 1 for now. And then do we want to wrap atoms or not?
Yeah.
So remember how like it was wrapping the atoms back. So let's keep that selected for now. Generate lattice. It's going to think for a little bit.
You're kind of thinking, oh, I like that.
It's amazing what you could do with ChatGPT now.
You make this all in ChatGPT.
Looks on.
Yeah, so there we go. So that gives us a nice little. Okay. So right now I have it colored by unit cell, but sorry, not by unit cell, by symmetry operator. But for certain applications, you might want to just show like the space that is occupied by atoms. So you might want to color everything the same. So if you just uncheck that color by symmetry operator, it should make it gray. Should. So
Did you say okay?
there we go.
Okay, good.
So this is useful if, let's say, you have two lattices, but they were solved in different space group, but you're not sure if they're actually the same or not. So what you would do is you'd render them both in black and white and just compare them side by side. But in this case, let's just keep the color by symmetry operator on. There's another option here. You could show grid points, where it just shows like the actual lattice grid. And then, okay, this is another useful part. So it's kind of tricky sometimes to perfectly line up your lattice. So you can use these 3 buttons here. So you can line it up along the A-B face, right? So this is A, this is B, or you can do down the AC face. So this is going to be A, this is C, or the BC. And so it perfectly lines up the view so you can look down one of the axes. And that's pretty much it, except let's say you're actually let's do a real world example here. So we actually solved these 2 structures of PPRA, and they came out of like quite different conditions, and they actually looked quite different when we solved them, right? So this is so on the left you have 6 BDU, and on the right you have 6 MC6. Right? I think you'll agree that these look quite different. In PPRA speak, this is like an S interface, whereas this here is a P interface.
Wait, I had a question.
Yeah.
Like, is it just like how they pack that's different, or is the structure itself different?
Well, exactly. That's the question. So that's what we want to figure out. So we want to figure out. So the asymmetric unit of these are different. The unit cell parameters are different with slightly different operators. So the question is, are these actually the same lattice or not? So if we take a look, this, we generate it for this guy. Oops. Generate it for this guy. Generate it for this guy. And let's line up BC face. Actually zoom out a bit. What you'll find is that these are actually the same lattice. But maybe it'll be more easy if I turn off this coloring. Right, that is the same packing.
I don't know what I'm supposed to be looking for.
Sorry, I know this is tricky, but if you just focus on the empty space, so the empty space that isn't occupied by atoms, you can see there are these like kind of rings that are packed in together.
So in theory, you could superimpose those on one another, and they would not just look like the same structure in the asymmetric unit. In fact, it's the entire physical crystal that looks the same. So the packing that generates the physical crystal is the same. What's different is the mathematics of how the crystal was defined when it was solved.
Right, so if you look, the asymmetric unit, and this one is here, the asymmetric unit here is here, but then when you expand the whole lattice, it turns out, oh, actually, these are the same structures. So we can actually, like, let's say you want to show this on a paper. So I made it also like kind of easy to output some nice images. So if you click export views, it'll pop up with a new window here. And you could set a few things. So let's, how big do we want the output image to be? In our case, decided, let's say we want 1.5 inches roughly. This parameter here dictates how much is visible in the x direction and in the y direction. So let's just standardize this. So let's say, I don't know, we'll call it 500 angstroms. And if you click update viewport, it'll update to that. Let me show you what I mean. Like if I click 1000 angstroms, it disappears for some reason.
It's probably thinking.
Oh, because it zoomed. Okay, never mind. It zoomed out way further than what's actually. Okay, let's just call it 750 then. Let's see what that. There we go. So we'll just okay. We'll say 750 angstroms. Okay. We'll maybe set the DPI, how high of a resolution image we want. Set it roughly high. Do we want a ray trace or not? I would suggest clicking this on, but I'm going to keep this off because it takes a little while. And I'll click render. Oh, oops. I forgot to set the output folder.
Does the GitHub download have
instructions?
Yeah.
How long did this take you to make?
I mean, I've had like some version of this script since the DDRC paper, because like I needed it to make figures, but basically like last week I just put a GUI onto it. Which is surprisingly easy, actually. It's just the back end of it took a long time, but just putting a GUI onto it was pretty easy. So let's render that again. Okay, so after it renders, in whatever output folder you specify, it gives you like 6 pictures. It gives you like for each face a separate picture. So what we can do, just import that into here. Yeah.
Okay. So the fact that the lattice is the same between the two, but the asymmetric unit is different is based off of how the crystal was mathematically solved.
Yeah. This was like an arbitrary choice by whoever was solving the crystal structure. Because you can yeah.
Okay.
Yeah.
Arbitrary choice, so it's not like Phoenix or something that.
Phoenix does automatically select.
Yeah.
So okay, so which does that come back to one of my other questions with how it stack?
It doesn't change any of the physical properties.
Okay.
But it's just like if you have if you drew the points and you can actually define them in different. So the real question is there a wrong or right answer?
Yeah.
If you can refine it, it's not wrong.
Okay. Okay.
Alright, so let's. Alright, we're just gonna do the same for the other one, just so we can. Here.
Because you know you always get a list of possible space groups,
Okay. Yeah.
and sometimes they're basically identical.
Okay.
Sometimes they are identical. It's like, okay, how do we know for sure? Well, sometimes it's just you see if you can solve the structure and how well. If the refinement gets hung up in the 30s, then it's like, okay, the data is better than that. There's got to be something systematic.
Okay. Okay, got it.
Like nowadays, these programs are so freaking good, like amazing. They're better than anything I could ever judge by. Like for me, for sure, maybe Han could do a better job, or Alba, or someone who's like really hardcore crystallographer. But for us, actually, even Han, she was shocked. She hadn't used some of the updated Phoenix and the software processing for the data in the last synchrotron trip. She came over after you guys helped her, and she was like, I can't even believe this. Why did I spend my entire life learning?
Well, until this point, you had to.
Yeah. Yeah, it's very, the symmetries part is, for me, was the hardest part of trying to learn crystallography.
But anyway, so once we like output these lattices, you can kind of compare them side by side on whatever your program of choice is. So you just output these images. You can see even though the asymmetric unit is different, the actual lattice is exactly the same. And this doesn't look very nice because this wasn't ray traced, right? If you were to click the ray trace button, it ends up looking really nice. So like here's some examples of like ray traced images. Like they actually do come out looking kind of nice. You can start comparing different lattices.
Oh,
This one was cool. I like this one.
Thought.
Yeah.
I feel like those are very large gaps. Like, they're also, that looks odd to me.
It is. And so, okay, that brings us to an interesting thing. If you look at all the gaps and compare it to the volume of those gaps and compare it to the volume of the protein, and you do that for every single crystal in the entire PDB, the vast majority of protein crystals will always have a solvent content of 50%, meaning that 50% atoms, 50% empty space, which is not really empty space, it's disordered solvent, but that's what those gaps are. And so any deviation from 50% usually should be viewed with skepticism, because it's like, are you missing something? So this one, you notice, yeah, there are huge gaps here, which led to a solvent content of 73%.
That's really, really, like there are very few crystals that are like that.
And so, believe me, this definitely made me raise my eyebrows when I was solving this, but there truly wasn't anything in here. And this led to a very, very low resolution. This led to a resolution of 6 angstroms because it has a low solvent content. Usually if you have high solvent content, lower resolution, because it's like the crystal isn't held together as nice, whereas like lower solvent content, you have high resolution. Like here's a good example. There's another one that was solved here that's the opposite direction. Like this one here had a solvent content of 23%.
That's really, really, really.
But then it had a resolution of 1.3 angstroms.
Okay.
So
the very first crystal I ever solved was 76.
Solvent content?
Yeah, and the best we could do was like 3.2 or something.
That's really good.
But yeah, for that solvent content. But C2 space group.
Yeah.
That's why I like the inquiry group.
guys have CTs.
Yeah, so that's pretty much it. I could send everyone this link if you want to play around with it. Also, I apologize. I've only tested this on Windows. I haven't tested it yet on like Mac or Linux. So if it doesn't work on Mac yet, let me know. I'll play around with it. But you can also just do this on our Windows server through no machine. So feel free.
One of these days I have to figure that thing out before Rob graduates. That's so cool.